This video will talk about transformations in geometry. In this video we're going to be covering how to do transformations and then also how to identify them based on a given graph with a pre-image and an image. So the first thing that we need to talk about are the different types of transformations. We have two different types. One is a rigid motion and then the other one is a non-rigid motion. So rigid motions preserve distance, or in other words, length or size. Meaning once we perform a transformation such as a translation, reflection, rotation, distance or size is preserved. The shape that's being transformed does not get bigger nor smaller. It stays exactly the same. The first of these transformations that are rigid motions is the translation. And a translation is a slide. So you can think of a movement up, left, right, down, and we're translating by adding or subtracting to the x and y values. X's move left and right, y's move up and down. The next one that we have is a line reflection, which is a flip. So here we're taking triangle ABC and flipping it over line K to map onto A prime, B prime, C prime. The next one we have is a rotation. A rotation is just simply a turn. If we have positive degrees, rotate positive 90, that means that we are rotating in a counterclockwise direction, going against a regular clock. Then the last one that we have is a point reflection. This is the same as a reflection, or most often we do this as a reflection through the origin, which is the same as a rotation of 180. You can see that turn happening here from quadrilateral MATH to quadrilateral MATH with all the primes there. So we're just simply turning 180, or in other words, reflecting through a point, namely the origin. The other type of transformation that we have is a non-rigid motion, which means it does not preserve distance. The important part here, again, does not preserve distance. And the only type we have here that's a non-rigid motion is a dilation, because a dilation is a shrink or a grow. And we do this by multiplying by some scale factor, say k. Now, if k is bigger than 1, meaning a number like 2, 3, 2.5, 5.7, doesn't matter. As long as it's bigger than 1, the object will grow. If k is between 0 and 1, meaning like 1/2, 1/3, 1/5, 2/5, then the object will shrink. It's getting smaller. A couple other pieces of important information are the following. Next being orientation. Orientation is the order of the letters. So for example, you can see here in this picture that a reflection was performed, reflection over a line, and when we read the letters starting at A, going counterclockwise, we get A, B, C. Now if I do that same thing, starting at A prime, reading counterclockwise, we get A prime, C prime, B prime. The order of the letters is not the same in a reflection over a line. So here orientation is not preserved. Next we have transformations off of the grid. So here we were asked to bring triangle ABC onto the double primes. So first we had to rotate around point A 180 degrees, then we had to translate along some vector. That vector is just telling us where we start and where we end. So once we rotate, we end up with this purple triangle right here. And I want to take point A and bring it to point A double prime. So we're translating along a vector. It looks like this. We could also reflect, if we needed to, reflect over line segment XY. Notice in each of these examples we are being very specific. You don't want to leave the reader to guess what you're trying to get them to do in order to complete the transformation. Next we have rotational symmetry. Order is the number of times an object can be rotated to map onto itself. Usually this is the number of vertices, if the figure is regular, meaning all sides and all angles are congruent. So something like a square or this regular pentagon that we have here. or an equilateral triangle. So if we are trying to rotate this pentagon onto itself, then the order would be 5. We can turn it 5 times around so that it maps onto itself. And to figure out that degree of rotation, how many degrees must it be turned to map onto itself one time, we take 360 and we divide it by the number of times it can rotate, meaning its order. So in this case, it's 360 divided by order of 5, which then gives us that 72 degrees that you see here. So these questions have been on Common Core exams in the past, whether it was June, August, or January. So we're going to start with number 1 here. It's just talking about properties of transformations. The vertices of triangle JKL have coordinates J, K, and L. You can read those coordinates. If you choose to, you can plot them. However, for this particular question, it's not very helpful because it goes on to say which transformation is the image JKL not congruent to the original. So again, not congruent, meaning size, distance is not preserved. Okay, so I'm going to suggest that for each of these types of problems that you try them on your own, and as you try them, pause the video. Then hit play, I'll explain them, and I'll tell you the right answer. Okay, so when I'm reading through my choices here, I see a translation, and I know that a translation is a slide. And when I simply slide a triangle, the distance is preserved, so choice 1 is out. Choice 2 says that we have a rotation. It doesn't even matter how many degrees we're rotating because a rotation is just simply a turn. When we turn a triangle, distance is preserved, so choice 2 is out. Number 3 says that we are reflecting. Whether it's a reflection over an axis, a line, or a point, distance is always preserved because a reflection is just a flip. If we flip a triangle over a line, distance stays the same. Choice 3 is gone. So now that leaves me with choice 4, dilation, with a scale factor. It doesn't even matter what the scale factor is, but as long as we know that a dilation is a shrink or a grow, then we know that distance is not preserved. So choice 4 is correct for number 1. Number 2 says in the diagram below, congruent figures 1, 2, and 3 are drawn. Which sequence of transformations maps 1 onto 2 and then 2 onto 3? So first we have to go from figure 1 over here to figure 2. Then from figure 2 over here to figure 3. Again, if you want to pause the video at this point so you can try to figure out the answer yourself, that would be great. It's great practice for you to do on your own first, and then check back in to get some feedback. So first I'm looking at this and I'm saying, okay, I have to take A, shift it up and shift it over. Take B, shift it up, shift it over. Take C, up, over. So if we are moving up and over, this is a slide. Then for the next part, part 2, it looks like we're taking A and swinging it around over here. Take B, swing it around over here. So if we're doing some swinging, some turning, then we have a turn. So now I just have to go through and match up what I have here in my choices with what I found on the picture. A reflection followed by a translation. So a flip, then a slide. We clearly did no flipping, so 1 is out. Number 2 says a rotation followed by a translation. So first turn, then slide. We did this, but in the opposite order. So if I can find translation, then rotation, that should be our choice. So choice 4 is our answer. Number 3 says which regular polygon has a minimum rotation of 45 degrees to carry the polygon onto itself. Now here it says regular, which means all sides, all angles are congruent. I'm going to go through each of these options and write out the number of sides that it has because that's what we're going to be looking for when we use that formula that we learned earlier. 360 over n equals the number of degrees. So octagon, octa, octopus, 8. That's an ugly 8, I'm sorry about that. Decagon, like a decade, is 10. Hexagon, I have no tricks for that. That one's just 6. And pentagon, like in Washington, D.C., the Pentagon has 5 sides. So here, if I have 45 degrees, I'm going to choose to put this over 1. So then this way it makes it nice and easy. We can just simply cross multiply. So now we have 45n equals 360. When we divide, we end up getting the number of sides. So n equals 360 divided by 45. Type it in the calculator if you need to. We end up with 8. N equals 8, so choice 1 is our answer. Number 4 says, in the diagram below, a square is graphed in the coordinate plane. A reflection over which line does not carry the square onto itself, meaning when reflected, it will not land on top of itself. Again, we're looking for the not here. That's the important part. So if we were to draw in the line x equals 5, I go over to where x is 5, 1, 2, 3, 4, 5, and then I just draw that line right in there. X equals 5. So my next step is to actually do the reflection. If the square lands exactly on the original 4 vertices, 1, 2, 3, and 4, then that is not our choice. However, if it does not land on those 4 vertices, then it is our choice. So when I do this reflection, I'm going to count boxes. So you're going to see me using like a laser tool here, if I can. Let's see. Okay, so we're going 1, 2, 3, 4, 5, 6. And I'm going to count the same number away from that line. 1, 2, 3, 4, 5, 6. So we're going to land just off the grid a little bit. And then the same thing should happen down at the bottom. You know, this vertex here is 6 away from the line, so I go 6 outwards, which means that if I draw in the reflected square, it does not land on top of itself, which means that choice 1 should be our answer. But let me just talk to you about a couple of the other ones here. Y equals 2, so I'm going to go up to 2, and then I'm going to plot my line going horizontally this time because it's y equals. And if I were to do a reflection here with these vertices, I'll put them in yellow now. This first yellow vertex is 3 away. 1, 2, 3. So I go 3 beyond it. 1, 2, 3. Which means it lands exactly on top of another vertex that we wanted to stay in the same position. The same thing happens on the right-hand side. 1, 2, 3. 1, 2, 3. Boom. This square is now landing exactly on top of itself. So that's why choice 2, y equals 2, is not our answer. Okay, now the next one says y equals x. That's the line where we go up 1 over 1 starting at the origin. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. You can see that that's the diagonal here through the square. And I know it's hard to reflect through a diagonal, but all that happens is the vertices switch. Meaning this point over here at 5, 1, negative 1 rather, and this one here at negative 1, 5. When they are reflected over this line, they switch, boom, boom, which means that now I get negative 1, 5, and this switches 5, negative 1, which is exactly where the original points were located. So choice 3 is not our answer. And then I just want to talk to you about this last one here. It says that x plus y equals 4. A lot of students chose this because it looks different than the other choices. However, this is not your answer, and you're going to see why in just a second. When I get this in y equals, by subtracting x, we now have y equals negative x plus 4. So we start at positive 4, and we go down 1 over 1, down 1 over 1. So now we're landing on the other diagonal. And if I were to use that same method as before, reflecting through this diagonal means that we are swapping positions. Okay, we're going perpendicular to the original line, which means that choice 4 is not our answer. So again, choice 1 is the correct answer for number 4. Number 5 says, in the diagram below, which single transformation was used to map A onto B, triangle A onto triangle B. You can see here that this vertex at the very right is being turned to map onto the vertex at the very top here. Notice I said the word turn. One of these 4 choices means turn. If you want to pause the video for a second, choose the choice that you believe is occurring here, then replay. A reflection, line reflection, is a flip. Rotation is a turn. Dilation is a shrink or a grow. And a translation is a slide. So again, we see a turning motion happening here, which means that we have a rotation. Number 6 says, in the diagram below, AC is congruent to DF, and we can see that that's already actually marked here for us. And points A, C, D, and F are collinear on line L, meaning on the same line. You can clearly see that they are all on line L. Let D prime, E prime, F prime be the image of triangle DEF after a translation along L, such that point D is mapped onto point A. So D is going to slide over here to point A. But if DF is congruent to AC, then F must land here. So now we have D prime, F prime, and then of course E prime would be somewhere up here. Okay, so now it says determine and state the location of F prime. Well, we just said F prime is on C. Because, okay, so now we're thinking, okay, what's a translation do? Translation preserves distance, and since AC is congruent to DF with D mapping onto A, F must map onto C. Part B says, let D double prime E double prime F double prime be the image of triangle DEF prime after a reflection across line L. Suppose that E double prime is located at B. So what they're saying now is that we're going to take and reflect the orange triangle on top of this purple triangle. Is triangle DEF congruent to triangle ABC? So is the original congruent to the new? Again, you can pause the video if you choose to. I think it's very helpful to pause it as you go so that you get a chance to think about these questions, because of course I already know how to do them, but you're the one that's going to be taking the test again in June. So here, if I were to think about whether or not these two triangles are congruent, first we had a translation, second we had a reflection. Neither of them is a dilation, which means that distance is preserved. So I'm going to say yes, because a translation along line L and a reflection across line L preserve distance, creating congruent triangles. So again, distance is preserved, but notice this important piece of information. Not only did I say a translation, but I was very specific about it. Remember, we talked about being specific about what is occurring. Translation along line L and a reflection across line L. If you are not specific enough on some questions, they will take off points. For example, there was a 4-point question in January that needed students to be very specific about what occurred and why triangles were congruent. If you didn't specify what transformation occurred along line L, across line L, you lost points. So the more specific you are, the better off you're going to be. Number 7 here says, which transformation would result in a perimeter of a triangle being different from the perimeter of its image? So that's like having this little small triangle where we add up the 3 sides here and say get a perimeter of, I don't know, 20. Then we have another triangle where we add up the three sides, but this time we get a perimeter of, say, 60. So which one of these would give you perimeters that are different is what they're asking. If we simply switch the coordinates, that's not going to give us a different size. If we negate one of them, if we negate one, that again will not give us a different size. However, if we take coordinates and multiply by 4, so say 1, 1 now becomes 4, 4. And, 2, 3 now becomes 8, 12. If I were to plot 1, 1 on a graph and over to up 3 on a graph, this is my little line segment. Then if I plot 4, 4 over 4 up 4 over 8 up 12. Now this second line segment is much larger than the first one, which means if I am multiplying, then my distances change. My perimeters get different. They get larger or smaller, but in this case they get larger because it's a multiplication of 4. Now if I were to do the same type of thing for number 4, choice 4, where I'm just adding 2 and subtracting 5, then instead of 4, 4 and 8, 12, I would now have 3, negative 4, and 4, negative 2. 3, negative 4, and, oops, I went the wrong way. 3, negative 4, and over 4, down 2. This is the same size as the original. So here again, choice 4 is not our answer. Simply adding and subtracting is just a slide. Multiplication is where that dilation comes in. Just going to erase this so we have some room for our next one. Last question on your notes today. It says, if triangle ABC is dilated by a scale factor of 4, which statement is true of the image of A prime, B prime, C prime? So when I see questions like this, I always like to sketch a right triangle. Oops, no primes, not primes, just ABC. And I always call it a 3, 4, 5 triangle. 3, 4, 5. Then it's dilated by a scale factor of 3, which means it's getting larger to make A prime, B prime, C prime. And if we're multiplying by 3, that means A prime, C prime is 9, 4 times 3 gives us 12, 5 times 3 gives us 15. So looking at our choices here, we have 3 times A prime, B prime, so 3 times 12 is equal to AB, 4. Well, clearly this is not true. 3 times 12 is not equal to 4, so choice 1 is out. B prime, C prime, so 15, is equal to 3 times BC, which is 5. 3 times 5 is 15, so this should be true. Choice 2 should be our answer. The next one says that measure of angle A prime, which is a 90-degree angle, is 3 times measure of angle A, which was 90 degrees. This is not true, so choice 3 is out. Then same type of thing here, angle C, we don't have an actual value for it, but angles are congruent in a dilation. So again, choice 2 for number 8. Again, all of these questions have been on Common Core exams previously, so they are good practice problems. You have more practice to do independently. If you want to pause, rewind, go back, revisit any of these problems, please feel free to do so. Otherwise, enjoy your transformations.